So now we know we will need n equations to solve for the coefficients in our approximation to the displacement function. So to do that, we will need to have appropriate definition for our weight functions. So we'll need n such weight functions, right, in order to get n equations representing the weak form, right? So there are various methods to consider the types of weight functions, the characteristics of the weight functions, etc. So very first method that we will consider today is the Galerkin method. Okay, in Galerkin method, our weight functions are assumed to be equal to our constituent function in the approximation to the u phi I. And because of such unique assumption, where wi is equal to phi I, we end up with a very special property for our stiffness matrix. So to do that, let's consider our term which is unknown. Okay, so I'm gonna write the term in our weak form which is unknown, which is negative of e integration over the domain wx and summation of ci phi x d omega, right? Now since we are using Galerkin method, we can write this as e times the integration of, let's say we are considered the first function phi 1 x times the summation ci phi x, and I'm just gonna simplify the domain term as simple 1D problem and write it as dx. And then I'm going to expand this for simplicity. Integration over the domain phi1x times c1 times phi1x dx plus the integration of phi1x times c2 times phi2x and all the way up to phi1x times cn times phi(n)x dx. And I can rewrite this term as e times, I'm taking c1 out of the integral because it's a constant, it does not depend on x, and then I can write the inner product of these two functions, phi1x plus c2 times the inner product of phi1x and phi2x and so on, right? I'm going to write this now in a matrix form. Okay, and to do that, let's write our row vector as the inner products, the phi1x with phi1x. The second term is phi1x with phi2x, the inner product, and the last term is phi1x inner product with phi nx. Multiplying this row vector is now our column vector, which contains all the coefficients c1, c2, cn. Notice that there are n elements to this row vector. So this is 1 cross n dimension, and our column vector is n cross 1. So multiplying these two vectors will give us a matrix of dimension 1 cross 1, which is a scalar. Okay. Similarly, we can write for our second choice of weight function. Let's say W2 is equal to phi2x. Then we can write our integration of W2x W2x times U2x dx as minus e times the row vector phi2x with phi1x. The second term is the inner product of phi2x with phi2x. And the last term is phi2x inner product with phi(n)x times the column vector containing all the coefficients. Okay, and similarly we can write it for the nth weight function equal to phi(n)x we can come up with an equation Wnx ux dx is equal to minus e times the row vector of the inner product of phi(n)x with phi1x and all the way up to phi(n)x with phi(n)x and the column vector c1, c2 to cn. Okay, now notice that we have n equations and such equation, and the vector containing all the coefficients. So we can condense this n equation into a matrix form, okay, and that would look like the matrix multiplied with negative of e. The matrix, all the elements are the inner product of phi1x with phi1x, phi1x with phi2x, the way up to phi1x with phi(n)x. Similarly, the second row of matrix would be the second equation, for which our weight function was phi2. So then we'll write the following inner products. Similarly, for the nth equation, we'll end up having the following terms. So now this matrix multiplied with the column vector containing all the coefficients. So let's call this matrix our stiffness matrix, and let's call this our the coefficient matrix. Now if you observe our stiffness matrix, you will notice that any term Kij, which is equal to negative E times the inner product of Fix with Fjx, which you can also write as negative E times the inner product of Fjx and Fix, which is then equal to Kji. This property says that our matrix K here is symmetric. And this is the special property of Galerkin method, which stems from our assumption that our weight functions are equal to our constituent function in the approximation to U phi, which indeed results in the matrix being symmetric.